Today, we're really tackling a big one. We're going on this journey into how reality itself works through the eyes of Albert Einstein.
That's right.
We're talking, of course, about his theory of relativity. If you've ever wondered about black holes or why your GPS is so accurate or just how space and time work together, well, you're in the right place.
hmm
Our mission today is simple. Cut through the jargon, pull out the really crucial bits from our sources, find some surprising facts, and basically get you totally up to speed on one of science's biggest ideas.
Absolutely. And maybe, first off, it's good to clarify, theory of relativity isn't just one theory. It's actually two related theories from Einstein.
What?
There's special relativity from 1905, and then general relativity, which came about 10 years later in 1915. And a little bit of trivia,
Mm.
Einstein didn't actually coin the name theory of relativity. In German, Relativitätstheorie. That was Alfred Bucherer in 1906. He kind of built on Max Planck calling it relative theory.
Huh. Interesting. Didn't know that. But the impact.
Mhm.
Wow. These ideas completely changed physics, astronomy, everything in the 20th century.
Completely.
It wasn't just tweaking Newton. It was like replacing a 200-year-old foundation with something totally new.
It really was a revolution.
Yeah.
And the concepts it brought in were just mind-bending at the time. You've got four-dimensional space and time woven together.
Right.
The idea that simultaneity is relative, time dilation, both kinematic and gravitational length contraction, these weren't just small adjustments.
And they led to practical things too, right? Not just theory.
Hugely practical. I mean, it paved the way for the nuclear age, gave us a much deeper grasp of elementary particles.
Yeah.
And looking out into the cosmos, it predicted things people couldn't even imagine back then.
Like black holes.
Exactly. Neutron stars, black holes, gravitational waves, things we've now actually observed and confirmed. It's pretty staggering.
Okay, so let's start with the first part then, special relativity. What's special about it? What's its domain?
Right. So special relativity deals with the structure of space-time, but specifically when gravity isn't a factor. You ignore gravity, basically.
Okay.
It came out of Einstein's 1905 paper, a famous one, on the electrodynamics of moving bodies. And it rests on just two fundamental postulates, two starting points.
Which are?
First, the laws of physics are identical for all observers who are moving uniformly. That means not accelerating. They're in what we call an inertial frame of reference.
An inertial frame. Would you just quickly unpack that?
Sure. Think of someone just floating in space, perfectly still, or maybe drifting at a constant speed in a straight line. No acceleration.
Got it. Still or constant velocity.
Exactly. For all those observers, the laws of physics look the same. Now, the second postulate, this is the really wild one. The speed of light in a vacuum is the same for all observers. Doesn't matter how fast you're moving towards or away from the light source or how fast the source is moving. You always measure the same speed.
Wait, that sounds wrong. Intuitively.
Completely counterintuitive. And that's where all the bizarre consequences come from.
Right. This is where it gets really interesting, isn't it? These two simple-sounding ideas lead to, well, weirdness.
They really do. For instance, the relativity of simultaneity. Two events happening at the same time for me might not be simultaneous for you if we're moving relative to each other.
So now isn't universal.
Pretty much, yeah. Then there's time dilation. Clocks that are moving relative to you, they tick slower than your stationary clock.
Time actually slows down.
As measured by you, yes.
Yeah.
And length contraction. Objects moving past you appear shorter in the direction they're moving.
Okay, mine's starting to bend a little.
Yeah. And another big one. There's an ultimate speed limit. No object, no information can travel faster than light in a vacuum.
The cosmic speed limit.
Precisely. And of course, the most famous equation maybe ever, EMCR.
Mass and energy are the same thing.
Equivalent, yeah.
Yeah.
Interchangeable. Mass is a super concentrated form of energy. That insight is fundamental to, well, everything from nuclear power to understanding stars.
Wow.
And just to add, mathematically, this meant throwing out the old way of adding velocities, the Galilean transformations, and replacing them with something called Lorentz transformations. That's the math behind the time dilation and length contraction effects.
Okay, so Einstein comes up with these radical ideas. But how do you actually prove something so counterintuitive? You said it's a principal theory based on observation.
Exactly. It's not just abstract math. It started from observed principles like the constancy of the speed of light, and it made specific, testable predictions. If the predictions hold up, the theory gets stronger.
So what were the key tests for special relativity?
There were three really crucial experiments. The first big one was the Michelson-Morley experiment. It did it initially in 1881. then a more famous version in 1887.
Ah, I've heard of this one. Trying to find the ether, right? This invisible stuff light was supposed to travel through.
That was the idea. They built this incredibly clever device, an interferometer, to detect the ether wind, the motion of the Earth, through this supposed ether. They found nothing, a null result. No matter how they oriented the device or what time of year, the speed of light was always the same in all directions.
Which was a huge shock.
A massive puzzle for physicists at the time. It basically killed the simple ether theories. People tried to patch it up with ideas like length contraction, the Fitzgerald-Lorentz contraction,
Yeah.
but it was Einstein who provided the solid theoretical framework for why there was no ether wind.
So Michelson-Morley didn't prove relativity, but it created the problem relativity solved.
You could put it that way, yeah.
Yeah.
It provided crucial evidence against the old view. Then came the Kennedy-Thorndike experiment in 1932.
What was different about that one?
Michelson-Morley showed light speed was the same in different directions, but Kennedy-Thorndike was designed to check if the speed itself changed depending on the observer's velocity through space. Again, using an interferometer, but a modified one.
And the result?
Another null result. It confirmed that the round-trip time for light, and therefore its speed, is the same in all inertial frames. It added another piece supporting Einstein's postulates.
Okay, 2 null results supporting the weirdness. What was the third experiment?
That was the Ives-Stilwell experiment, done in 1938 and 41. This one was different. It wasn't a null result experiment. It was designed to directly measure time dilation.
How?
They looked at light emitted by fast-moving ions. Special relativity predicts something called the transverse Doppler effect, a shift in the light's frequency purely due to time dilation, related to the Lorentz factor.
And did they see it?
They did. They measured the frequency shift, and it matched Einstein's prediction perfectly. It was the first direct quantitative confirmation of time dilation.
Wow. So Michelson-Morley gets rid of the ether, Kennedy-Thorndike confirms light speed is constant, and Ives-Stilwell directly shows time slowing down.
That's a good summary. Together, these experiments built a really solid empirical foundation for special relativity. It wasn't just a neat idea anymore. It described how reality actually worked, at least in the absence of gravity.
Right. Which brings us neatly to the other half. General relativity. The gravity part.
Exactly. This is where Einstein tackled gravity, and he started with a really profound insight. The equivalence principle.
Equivalence. What's equivalent?
The feeling of acceleration, like being pushed back in your seat when a car speeds up, is fundamentally indistinguishable from the feeling of gravity, like standing still on Earth. Locally, you can't tell the difference.
Huh, okay.
And the implication is huge. It means that free fall, like an astronaut floating in orbit, isn't really feeling zero gravity. It's actually inertial motion. They're following the most natural path possible through space-time. Gravity isn't a force pulling them. It's the path itself.
So objects fall because the path is curved, not because of a force.
Precisely. To make this work, Einstein realized space-time itself must be curved by the presence of mass and energy. He teamed up with a mathematician friend, Marcel Grossmann.
Right, you mentioned geometry earlier.
Yes, they used Riemannian geometry, a type of math perfect for describing curved spaces. And by 1915, Einstein had developed the Einstein field equations.
The core of general relativity.
Yeah, that's right. These equations are the mathematical heart. They show exactly how the distribution of mass and energy in a region dictates the curvature of space-time around it.
And like special relativity, this leads to some pretty wild consequences, right? Curved space-time isn't exactly intuitive.
Not at all. But it makes incredible predictions. There's gravitational time dilation clocks tick slower, deeper in a gravitational field, so a clock at sea level runs slightly slower than one on a mountain.
We actually measure that.
Oh yes, with atomic clocks, absolutely. Then there's the precession of orbits. Newton's laws predict stable elliptical orbits, mostly. But GR predicts tiny shifts, or precessions, especially in strong gravity.
Like Mercury.
Mercury's orbit was the classic example. Its orbit precesses slightly more than Newtonian gravity could explain. GR nailed the difference perfectly. We also see this dramatically in binary pulsars.
What else?
Light deflection. Gravity bends light. Mass curves space-time, and light follows that curve.
The famous eclipse experiment.
Exactly. Eddington's 1919 observations during a solar eclipse showed starlight bending around the sun, just as predicted. Huge confirmation. There's also frame-dragging rotating masses literally drag space-time around with them.
Like stirring honey.
Kind of, yeah. It's a very subtle effect, but we've measured it. And on the grandest scale, GR underpins cosmology, the expansion of the universe, even accelerating expansion. It all comes out of these equations.
So, given how revolutionary this theory was dealing with gravity itself, was it accepted quickly, like special relativity seemed to be after the experiments?
Actually, no. General relativity had a tougher time initially. For one thing, the math was, well, really hard. Very few people understood it deeply back then.
Okay, that makes sense.
And for a long time, it seemed like its predictions were mostly tiny corrections to Newton's gravity, hard to measure and maybe not that practically useful beyond, say, Mercury's orbit. It felt a bit like a theoretical curiosity to many.
So, when did it really take off?
Things started to change significantly around the 1960s. Partly, new mathematical tools were developed that made working with GR easier, more visual.
Right.
But the really big driver was astronomy. We started discovering things out there that Newtonian gravity just couldn't handle, but GR explained beautifully.
What sort of things?
Quasars, discovered in 63 incredibly bright distant objects powered by supermassive black holes. Then the cosmic microwave background radiation in 65, the afterglow of the Big Bang. Pulsars in 67, rapidly spinning neutron stars. And then finding actual black hole candidates starting in the early 80s.
All predicted or explained by GR.
Exactly. These discoveries showed GR wasn't just about tiny corrections. It described the most extreme environments in the universe. The theory suddenly became essential.
And those classic tests, like the light bending and Mercury's orbit, they solidified its place too.
Absolutely. Those initial tests were crucial. Besides Mercury's perihelion precession and the deflection of light by the sun, there was also the gravitational redshift of light losing energy climbing out of a gravity well confirmed in experiments. And ongoing tests keep confirming the equivalence principle and even frame dragging to higher and higher precision.
It's amazing how these incredibly abstract ideas hold up to scrutiny, which brings us to today. What does all this relativity stuff mean for, us, for you listening right now? It's not just history or astronomy, is it?
Not at all. It's easy to think of relativity as something exotic, only relevant for black holes or the Big Bang. But relativistic effects are real, and they matter for technology we use every single day. There's serious engineering considerations.
Okay, like what? Give us the big example.
GPS, Global Positioning System,
No.
or the European Galileo, the Russian GLONASS.
Yeah.
They all rely fundamentally on accounting for relativity.
Really? How so?
Okay, think about it. You have satellites orbiting way up high, moving really fast. So two things are happening. First, the satellites are moving at about 14,000 kilometers per hour relative to you on the ground. Special relativity says their clocks will tick slightly slower than yours because of that speed.
Okay, time dilation from speed.
Yep. But second, they're orbiting about 20,000 kilometers up, where Earth's gravity is weaker than it is down here on the surface.
And general relativity says?
General relativity says clocks tick faster in weaker gravity. So you have special relativity slowing the satellite clocks down, and general relativity speeding them up compared to clocks on Earth.
They don't cancel out.
Nope. The general relativity effect, faster clocks, is actually stronger than the special relativity effect, slower clocks, for GPS satellites. The net result is that the satellite clocks run faster than ground clocks by about 38 microseconds per day.
38 microseconds, that doesn't sound like much.
It's tiny, but GPS relies on nanosecond timing accuracy. If you didn't correct for those 38 microseconds every day, the positioning errors would build up incredibly fast.
Yeah.
We're talking kilometers of error within a single day. Your GPS would be completely useless.
Wow, so the phone in my pocket mapping my route is actively doing relativity calculations.
The system has to account for it constantly, yes.
Yeah.
Both special and general relativistic effects are built into the timing corrections. Without Einstein, no GPS.
That is genuinely mind-blowing. Are there other everyday, well, maybe not every day, but other important applications?
Sure. High precision timekeeping generally, which is vital for synchronizing networks, financial transactions, scientific experiments, that relies on understanding relativistic effects on atomic clocks.
Okay.
Electron microscopes. The electrons move so fast that their relativistic mass increase is significant. You have to account for it to focus the beam properly.
Right.
And particle accelerators, like the Large Hadron Collider, they push particles close to the speed of light. Their mass increases enormously, exactly as Amium seesaw predicts. The magnets that steer them have to be designed for these relativistic masses.
So it really permeates modern science and tech.
It absolutely does.
Okay, so let's wrap this up. We've gone from special relativity's core ideas, constant light speed, relative simultaneity, time dilation, to general relativity's curved space-time explanation for gravity. We've seen how experiments, from Michelson-Morley to eclipse observations, proved these bizarre ideas right. And now we see them at work in our GPS. What a journey.
It really is. And it underscores something important, I think. This kind of deep scientific knowledge isn't just for scientists. Understanding how these things work, even conceptually, helps us appreciate the world, and it's valuable. Applying critical thinking to this kind of complex information is key.
Absolutely. And maybe a final thought to leave you with. Relativity showed us our everyday intuition about space, time, and gravity was fundamentally incomplete, maybe even wrong. It makes you wonder, doesn't it? What other bedrock assumptions might be overturned next? What deeper mysteries are still out there, waiting for the next Einstein to unravel?